All right, welcome back, everybody. Today we are going to cover about 1.5 sections. This stuff is actually hyperbolic functions. Hyperbolic functions in general is what we're looking at. We're going to be doing the hyperbolic trig functions. This is actually in 6.9 in the book. They wait until we do chapter 6 in Calc 2. But Calc 2, you should have all the derivatives by then. And for some reason, they put the derivatives of the hyperbolic functions in chapter 6. So we're going to have them up here. Hyperbolic functions. We have hyperbolic sine goes by sinh, sine h. That's our hyperbolic sine. It's actually constructed, the hyperbolic functions are constructed with combinations of e to the x and e to the negative x. So that's how we list hyperbolic sine. Hyperbolic sine is sinh x equals e to the x minus e to the negative x over 2. Hyperbolic cosine, cosh x, is e to the x plus e to the negative x over 2. So there, it takes the average of it. Like cosh is the average. And sinh is the average of e to the x and e to the negative x, or negative e to the negative x. Now you might wonder why we're going to talk about this. I'll show you some images of hyperbolic things in reality. The fuck Eye of Sauron hat is that? That's fucking creepy as hell, Dalton. Fucking look up, there's an eye fucking staring at me. Big old fat fucking big red eye on his beanie. All right, let me show you guys what we're talking about here. This is probably the most famous hyperbolic thing that you know in real life. This is the Gateway Arch in St. Louis. It is a hyperbolic cosine inverted. It's upside down. It follows that trajectory. Other things that use it are catenary bridges, suspension bridges. They tend to be the smaller bridges. The big bridges like Golden Gate is a suspension bridge also, but it's made out of metal. It's so fucking heavy that it tends to follow more of a parabolic curve, the cables. But the cables on this follow a hyperbolic cosine. There's other ones as well. You can look at a catenary, they're called catenaries. A catenary arc. So like lots of cathedrals and stuff like that have them. Old structural temples. Where's a good one that's got the bricks? Oh, you can actually kind of see it a little bit there. But they build the bricks where they build it up and do stuff like that. So there's uses for it. So if we look at e to the x and e to the negative e to the negative x, this one is e to the x, this one is negative e to the negative x. When we average those, we get this. So that's hyperbolic sine. That looks a lot like x cubed. And then if we look at e to the x and e to the negative x, those are like that. When we average those two, we get hyperbolic cosine. Hyperbolic cosine looks a lot like a parabola, like x squared plus 1. It looks a lot like it. So if we did this negative, now all of a sudden we have the gateway arch. So those are some examples. Catenary arcs and bridges. When you're the trajectory of a spacecraft doing a planetary slingshot. Or lunar slingshot. We've actually used these to get a satellite deep into like out near Pluto and past and shit, using stuff like this because you can send it. If you know where Jupiter's going to be, you get the, and they do. They know where everything is. They can plan where it's going to be 9 months ahead and shit like that. They send it so that it gets pulled into the orbit, and getting pulled in the orbit of a planet speeds it up. And the speeding of it up makes it so it actually is going too fast to go into orbit, like stay in orbit, and it like shoots out. But the act of getting pulled in like accelerates the craft a little bit, it shoots out, and that pull of it going into the planet's orbit gets pulled in and it's going too fast and slingshots out. That is a hyperbolic arc as well. So there's plenty of function uses for them. Let's see. There's applications in special relativity. You all don't give a shit about that so much. Not yet, at least, unless you're going to go deep into physics. What we're doing in calculus is limits and derivatives and shit like that. So, what is the limit as x goes to, let's go with infinity on sich. Well, we can look at the graph. As x goes to infinity, this thing skyrockets to infinity. When it goes to negative infinity, it goes to negative infinity. Hyperbolic cosine does the opposite. Not the opposite, but they both go to positive infinity. So the limit as x approaches infinity of sinh is positive infinity. As it goes to negative infinity, it's negative infinity. And cosine didn't give a shit which side it was going to. The limit as x goes to positive or negative infinity of hyperbolic cosine is just positive infinity. And you can figure that out actually plugging them in up here. Separate it into 1/2 e to the x minus 1/2 e to the negative x. One of those goes to 0 and one of them goes to infinity. Any questions so far? People writing like crazy. Oh, be patient and wait. All right. So the hyperbolic functions, the trig functions, they actually behave like a lot like the trig functions. In most ways. We can do hyperbolic tangent or tanh. Just like the regular tangent, it's sine over cosine. In this case, hyperbolic sine over hyperbolic cosine. And when you clean it up, it's e to the x minus e to the negative x over e to the x plus e to the negative x. Hyperbolic cotangent is the same way as cotangent. We have cosh on top, hyperbolic cosine on top, and hyperbolic sine on bottom. And this just flips tangent over. Our secant function, 1 over cosh x is our hyperbolic secant function. And we literally just flip cosine over. So we got 2 on top and e to the x plus e to the negative x on bottom. And when we use the reciprocal of hyperbolic sine, we get hyperbolic cosecant. I do not have a good way of saying that one. They say sinh, tanch, cosh, sech, but like c-sech, I don't know. There's no fucking vowels in there. It's fucking, I don't know how to say it. There's a 2 on top. It's still got the e to the x and e to the negative x, but there's a minus sign. All right, so formulas and identities with these things. And they can all be proven, using the exponential definitions of them. We're going to do it for some of them. Well, one of them, just to illustrate it. These are all very similar to the trig identities, but they're just a little bit off. We used to have cosine of x, or cosine squared x, and sine squared x equal to 1, and we added them together. When we do the hyperbolic version, it becomes subtraction. So cosh x minus sinh, or cosh squared x minus sinh squared x equals 1. Yeah, but of them all, that's the one you need to memorize of the 3 that are going to be on this page, because the other 3 are all derivable from this. We used to have 1 and then tangent squared x related to secant squared x. We make it hyperbolic. It used to be addition. Now it's subtraction. You get this one by dividing the top one by hyperbolic cosine squared. And we used to have cotangent squared, cotangent, plus 1 equaled cosecant squared. When we make it the hyperbolic version, it's got the minus in there, not a plus. Ready for some more? Those are the base 3 from the squared ones. Then we have the sum and difference formulas. We have hyperbolic sine of x plus y. I'm going to do A and B. That might be better. This actually looks just like the regular version. Sinh A cosh B plus cosh A sinh B. Oops, gotta have the H's in there. And if you have a minus, it goes to a minus between them. Cosine's a little bit different. The hyperbolic cosine A plus B. The original one with cosine is cosine A, cosine B. So we've got cosh A, cosh B. And the original one changed signs. It had negative sine A, sine B. This one's going to have plus sinh A, sinh B. Verify this independently. Yep. when we had sine of 2x or sinh of 2a, it's the same format as the original. Sine of 2x is 2 sine x cosine x. This is 2 sinh a cos a. And when we have cos of 2a, this is just replacing, going up here, replacing b's with a's. That's effectively where this comes from. We get cos squared a plus sinh squared a. That one's a little different than the normal one. The normal one with cosine of 2a is cosine squared minus sine squared. So this one's slightly different than the original. The two cosine ones are, so I'm making note of that. These are slightly different than the originals. And then cos is an even function. Even functions, if you put in a negative value, it equals the same as the positive value. And sinh is an odd function. If you put in a negative value on an odd function, it spits out the negative of the irregular function. So let's prove cos of x minus y equals cos x cos y minus sinh x sinh y. All right, so what we have, let's just write down what each of them are. Cos x is e to the x plus e to the negative x over 2. I'll do the y, I'll do the x's in green and the y's in red. Cos y is e to the x, or it's not e to the x, e to the y plus e to the negative y over 2. And we're multiplying those together, and we got a minus here. Sinh x is e to the x minus e to the negative x over 2. Maybe I should put this stuff in parentheses. And since y is e to the y minus e to the negative y over 2. Now, both of these, when I multiply together, are going to have a denominator of 4, right? 2 times 2 is 4 for both of them. I'm going to put the 1/4 out front. And then we're going to distribute. E to the x times e to the y is e to the x plus y, like that. And then e to the x times e to the negative y is plus e to the x minus y. And then I add, now I'm doing inner, I'm doing FOIL, e to the negative x times y is negative x plus y is the exponent. And finally, we have both negatives right there. Negative x and negative y. All right, I'm going to distribute this negative into the first parentheses. So that'll make that negative and that becomes positive. So now it's easier, a little easier to track. I've got negative e to the x times e to the y is negative e to the x plus y. And then I multiply the last two. I've got negative e to the x times negative e to the negative y becomes plus e to the x minus y. There's a lot of shit going on here. You kind of got to go a little slow, right? Negative e to the negative x times e to the y. We add the exponents, negative x plus y. Wait, nope, that's a positive. That's not a negative. That's a positive right there. And then I have positive e to the negative x times negative e to the negative y is negative e to the negative x minus y. So I got some things that are negative. I've got a negative e to the x plus y. That's going to cancel the positive e to the x plus y. And I've got negative e to the x minus y. And so I need the positive one. That one cancels. So if I gather up what I have left, I have an e to the x minus y here and an e to the x minus y right there. I've got 2e to the x minus y. And I think I crossed off the wrong thing a second. I did. That wasn't supposed to be crossed off. That was supposed to be crossed off.
Question.
That was your, sorry, I didn't even see your hand. My bad. If I don't respond to your hand being up, say something. I'm clearly in the zone. This one goes with that one, and there's two of those. So I've got 2 on each of these. This is the 2 over the 4 puts a 2 on bottom. And I have e to the x minus y plus e to the negative x plus y. And I'm gonna rewrite that. I'm gonna check this out. We still got the e to the x minus y. I'm gonna factor out a negative on the exponent right here, and that'll be negative x minus y. Why do I have a negative here? What did I fuck up? That should be a minus sign in there, and it's not. Or I'm wrong. Because this looks like cosh of x. Oh no, I'm right. It's cosh of x minus y. The negative's up there. That's fine. Like if I did this as e to the theta plus e to the negative theta over 2, that would be cosh of theta. Well, theta here is just x minus y. It's a little trippy. But we started with the right side and we ended with the left side. You will go into these at some point. I'm just bringing them up now so you've seen them before. His name is Euler. It doesn't look like Euler. It's Euler. E is named after him. We use the letter E for exponent. The E is for Euler. Euler's formula, we have e to the plus or minus ix equals cosine of x plus or minus I sine x. So these are somewhat related to these. In that you'll see that cosine x equals e to the ix plus e to the negative ix over 2. And sine x is e to the ix minus e to the negative ix over 2. So it gives us a relationship between trig and complex exponents. All right, so why don't we actually get to some calculus shit? We talked about the limits earlier, but like, what do you care about here? Derivatives. So let's do the derivative of cosh x. This is the derivative with respect to x of e to the x plus e to the negative x over 2. This might be easier to see as not doing one fraction, showing it like this: 1/2 e to the x plus 1/2 e to the negative x. What's the derivative of e to the x?
Yes.
Is e to the x, yeah. What about the derivative of e to the negative x? Yes, Dalton. Negative e to the negative x. There's a chain rule going on there. You take the derivative of e to the x, but then you got to take the derivative of the where the x is at. And it's negative x, so you'll have a -1. So this turns into the derivative of, nope, derivative is already done at this point. 1/2 e to the x minus 1/2 e to the negative x. So if I put that all back together, I have e to the x minus e to the negative x over 2. That's hyperbolic sine. It's not negative. Derivative of cosine is negative sine. Derivative of hyperbolic cosine is just positive hyperbolic sine. So it like, when you're dealing with the hyperbolics, it follows the trig shit, but there's like some little quirks with negative signs in there. Why don't you guys work out hyperbolic sine? Take a gander at that bad boy. Then we'll do it together. Probably goes surprisingly quick. A little bit longer. You should get e to the x, and then the negative from the e to the negative x comes down and cancels out the negative out front, plus e to the negative x over 2. So this is cosh x. So they're the derivative of each other, just like sine and cosine are, but there's no change in signs. All right, so let's make a list of them. Does anyone need that up longer? Okay. So all the ones that stay positive. We've got the derivative of cosh x equals sinh x. We have the derivative of sinh x equals cosh x. And since they're both positive, we know tangent is sine over cosine. Oops. ddx of hyperbolic tangent is hyperbolic cotangent. No, it isn't. What the fuck am I talking about? It's the secant squared. Hyperbolic secant. Over here talking out my ass. So they have the same setup as the original trig functions. When you do the derivatives, like derivative tangent is secant squared. You just got to pay attention to the signs. All the ones that go negative are the other ones. Derivative of secant x, or hyperbolic secant x, is negative secant x tangent x, or hyperbolic secant x, hyperbolic tangent x. The derivative of hyperbolic cosecant x is negative hyperbolic cosecant x, cotangent x, or hyperbolic cotangent x. And finally, the derivative of cotangent x is negative hyperbolic cosecant squared x. So they look like they're originals other than some sign shits. All right, that's a lot of information. So you guys want a 5-minute break now or after we do the inverse hyperbolic trig functions? Anyone need a break right now? All right, let's take a 5-minute break. All right, we're gonna take a look at the hyperbolic inverses. I'm gonna take us over to Desmos real quick. So hyperbolic cosine is that black parabola looking thing. When we swap x and y to get the inverses, we get a sideways parabola. But to keep it 1-to-1, we have to restrict y to be greater than or equal to 0. So there's going to be some restrictions on hyperbolic, the inverse of a hyperbolic cosine. If we look at sine, I'll write these down in a second. Sine only has one y value for every x value. So when we do its inverse, it's just fine. It's not going to have any restrictions. So pictorially, or we showed pictorially. So cosh inverse of x has a restriction. If the domain is going to be 1 is greater than 1 to infinity, and the range is 0 to infinity. Hyperbolic sine didn't have any restrictions on its inverse. Both domain and range were negative infinity to infinity. We look at tanh inverse. The domain here is negative 1-to-1. And the range here is negative infinity to infinity. Hyperbolic cotangent inverse has a fun domain and range. The domain here, they're both have unions in them. Domain is negative infinity to negative 1 in union with 1 to infinity. And the range is negative infinity to 0 in union with 0 to infinity. That's crazy. The only way spot the range does not exist for hyperbolic cotangent is at x equals 0. Because these seg don't include 0 right here. Hyperbolic secant inverse. Domain is 0-1. And range is 0 to infinity. And finally, hyperbolic cosecant. It also has one of those twofers. We've got negative infinity to 0 in union with 0 to infinity for the domain. And for the range, we have the exact same thing. You guys got those? Almost. I see pins still going on for a couple. Those are important to know. Here's our pact. Let's make a pact on the hyperbolic trig functions. I solemnly pledge to do all the homework in that section, and Mr. Jones isn't going to test me on it. Is that a pledge you all are willing to take? Because there's a lot of shit here. There's a lot of. I tried memorizing it. And I had a hard time memorizing it as a student. I did, but like then I never used it, and so I'm like, why am I fucking gonna do that to you? You use it so rarely that you just need to know that it exists. You need to know how to work with it. Because by the time you need it again, you aren't going to remember it. But when you know it exists, you know what to go look up. Okay? That's our pledge on this side. So don't get discouraged by all this shit that's getting thrown at you today. Because there's more. Like taking the derivative of the inverses isn't as easy as it sounds. So like I'm going to show you how some of these turn into other things. Let's just take a look at, let's start off with hyperbolic cosecant equals y. I'm going to show you how some of these, I'm going to show you how the first one's derived, then I'll just give you a list for the rest. This is the same thing as saying x equals cos y. And cos y is e to the y plus e to the negative y over 2. Well, I can clear fractions. And I can get everything on one side. I subtracted 2x from both sides, and then I just switched which sides they were on. E to the negative y is never 0 anywhere. Not 0 anywhere, so I can multiply by it. You never want to multiply by 0. If I multiply by e to the y here, not e to the negative y, e to the positive, both neither of them are equal to 0. But e to the y never equals 0, so I'm going to multiply by it, and I get e to the 2y. This goes to 1, so I'm going to put it at the end. Plus 1, and then I've got minus 2x e to the y. This looks a lot like u squared minus 2xu plus 1 equals 0, it's quadratic. Where u equals e to the y. So we're gonna use a quadratic formula, u, which equals e to the y. We've got a is 1, b is negative 2x, and c is 1. So negative b would be plus 2x. Then I've got plus or minus the square root of b squared, which would be 4x squared, minus 4ac, which is going to be minus 4. I'll write it out like that real quick. Then we're all over 2a is 2 times 1. Okay, so I've got e to the y equals 2x plus or minus. This inside here is 4x squared minus 4, which is 4 times x squared minus 1. So I can factor out the 4. The square root of 4 is 2. So e to the y is just x plus or minus square root of x squared minus 1. And we started in terms of y. We want to end in terms of y. We take the natural log of both sides. Natural log of e to the y is just y. We have natural log of x plus or minus square root of x squared minus 1. The negative portion is in there. Negative is to show for x values less than 0. But hyperbolic cosine doesn't have that. Hyperbolic inverse cosine doesn't have x less than 0. So we get rid of the minus sign. And what we end up with is y, which equals hyperbolic inverse of cosine of x, can be written as the natural log of x plus the square root of x squared minus 1. which is good because we know the derivatives of these. When we did the derivatives of the trig functions, we made triangles. The XY interpretation of it, a hyperbolic sine and cosine, uses the hyperbolas, and like showing the graphical representation on that is a bitch. It's not worth doing. It's better to switch to this version. So we can write equivalents of the hyperbolic inverses in terms of some crazy natural log functions. All of them. So let's write them all down. Oh, does anyone need this up longer? Wait, Matthew's still right? No. Everyone looks good. Okay. So these theorems are true for X in the domain of. So if we're outside the domain of the trig function or a hyperbolic trig function, it doesn't apply. We just showed cosh. Cosh inverse of X is natural log of X plus square root of X squared minus 1. Sinh is pretty close. It's the natural log of X plus the square root of X squared plus 1. Tanch inverse can be written as 1/2 the natural log of 1 plus X over 1 minus X. And the hyperbolic cotangent X is very similar. It's eerily similar. I'm going to put the X's first because the X on bottom, we do X minus 1 rather than 1 minus X. So only the bottom is different between those two. Just like the only difference between sinh and cosh is the negative inside the radical. Hyperbolic secant can be written as the natural log of 1 plus the square root of 1 minus X squared all over X. Do you see why I'm making this pack with you? Because y'all would have said, nope, fuck this class. Peace out, I'm dropping. No, maybe not all of you. Some of you do pretty good. Some of you would be like challenge accepted. And finally, the hyperbolic inverse for cosecant. We've got 1 over X plus the square root of 1 plus X squared over the absolute value of X. Ah, that's just fucking shitty. That's the worst one ever. So those are what they can be written as. And if we write them as that, we can take the derivatives. I will show you what the derivatives are when you're ready. Everyone ready? Okay. Derivative functions. Derivatives of hyperbolic inverse trig. It's a fucking mouthful, isn't it? Especially if I say hyperbolic inverse trigonometry, just like let's go the full name. Derivatives of the hits. There we go. The hits. HIT. I'm liking that. All right. DDX of sine inverse, hyperbolic sine inverse, is 1 over the square root of 1 plus x squared. I might make a bonus question related to this on the test. Because you don't need to know the other things to use these derivatives. So these are actually just flashcardable. The derivative of hyperbolic cosine inverse is 1 over the square root of x squared minus 1. But x has to be greater than 1. We have that domain restriction. Derivative of hyperbolic tangent inverse. Actually kind of easy thing to memorize. And here, this is the absolute value of x is less than 1. Or another way of writing that is -1 is less than x, which is less than 1. Let's get to the other three. Let's do cotangent, hyperbolic inverse. That can't be right. There's no way that's right. Oh, fucking A, it is. Who would have guessed? It's the same damn thing. The only difference is here, absolute value of x is greater than 1. So -infinity to -1 in union with 1 to infinity. See how long I kept that shit memorized? Take a look at the derivative of hyperbolic secant inverse. This is -1 over x times the square root of 1 minus x squared. With 0 is less than x less than 1. These are all just the domain restrictions we talked about on the other page on the right side. And the derivative of hyperbolic cosecant inverse and for that, x cannot equal 0. No. That one's positive. Check other ones. No, it is negative. I'm seeing mixed answers here. Okay. So. I mean, these might be, let's like do one of them. Show it. This might actually be easier if we do implicitly. Let's take a look at tangent inverse x equals y, and we want to find dy dx. And we're going to show that it equals 1 over 1 minus x squared. All right, first thing we'll do is we'll swap them. X equals hyperbolic tangent of y. And then we will do d dx of both sides. The derivative of the left is 1. The derivative of the right is, remember we got to do implicit differentiation. So it's like a chain rule here. Derivative of tangent is secant squared. And then we do the derivative of the inside is dy dx. So when we divide by secant squared, we get dy dx equals 1 over secant squared. Why? And we're going to use the trig identity here. This is 1 minus tanh squared y. And the reason why I do that, because we're going to plug this back in. We want to put y back in. And if I do it directly tanh inverse into tanh, they kind of cancel each other out. So we get 1 over 1 minus tanh of tangent inverse of x. And that is squared down there. So the hyperbolic tangent and the tangent, or hyperbolic tangent inverse, cancel each other out. We get 1 over 1 minus, all we're left with is the x, and it's squared. We're gonna start 3.4 in a second. It's called related rates. If you're gonna memorize anything of these, and it can't hurt, just do the derivatives. There's only 6 derivatives, there's 6 derivatives and 6 derivatives inverses. I would memorize those, you can flashcard those. And maybe knowing these 2 things right here. Those are worth knowing. The domain shit, you're never gonna remember it. Like, you could put it on a flashcard, but good luck. These bad boys show up a lot. Top 3. In Calc 2. They show up a lot in Calc 2. The inverse for sine, hyperbolic, sine, cosine, and tangent. All right. 3.4 is called related rates. You know what? I'm gonna make this 2 videos. I'm gonna hit stop record.